Then there's a program on the lever. Next comes mechanical advantage and friction. Then the screw and the wheel. And finally, the pulley. But our story begins with the inclined plane. You haven't really got enough force to lift that barrel, have you? How much force do you need to lift it? Well, how much does it weigh? So you'll need at least 800 newtons of force to lift it into the back of the truck. How far is that? About 1 meter? How many joules of energy will it take? Well, figure it out. Energy is the ability to do work. Work equals force times distance. 800 newton meters of work, or 800 joules of work, which is the same as 800 joules of energy. But you still can't lift the barrel. There's something wrong somewhere. Perhaps it's because you have to exert your energy all at once. If only you could load the barrel onto the truck a little bit at a time. If you could slice it into 4. Then you'd have 4 200-newton slices of barrel. And you'd only need 200 newtons of force to lift each one. That's easy, isn't it? You're using your energy more effectively now. You're spacing it out over a longer time. But you don't get anything for nothing. Although your force is cut down to a quarter of what you need to lift the complete barrel, each time you lift a quarter of the barrel, you exert that force through 1 meter. Which means that you lift the 4 quarter barrels through a total distance of 4 meters. What you're winning on the force, you're losing on the distance. It's a sort of trade-off. The greater the distance, the less force you need to exert. Very neat. But you can't go around breaking things into pieces just because they're too heavy to lift. If only you had a machine that would allow you to trade increased distance for decreased effort or force. Here's your machine. Yes, I know it's just a plank, but it's also a machine. Try and get the barrel into the back of the truck now, and you'll see why. Magic, isn't it? No, it isn't. It's exactly the same trade-off you got when you split the barrel into 4. The plank is 4 meters long. Instead of moving the barrel 1 meter by lifting it straight up, you're moving it 4 meters by pushing it along the plank. You only need to push it with about a quarter as much force, with only about 200 newtons instead of 800 newtons. But since moving 200 newtons through 4 meters is the same as moving 800 newtons through 1 meter, it will still take roughly the same amount of energy to move the barrel by either method. That's why we can call the plank a machine. It doesn't reduce the energy you need to do something, but it does help you to use your energy more effectively. You think you've just made a new discovery? Think again. How do you suppose they built the pyramids 5,000 years ago? They didn't actually use a plank, of course, but a ramp of earth, which is exactly the same principle. And you use the same principle yourself every time you stand on an escalator. Because the plank, the ramp of earth, and the escalator are all 3 examples of the same type of simple machine. They are all sloping, and they are all flat. So physicists call this variety of machine the sloping flat thing. Well, those aren't the exact words they use. They take the Latin-derived word for sloping, which is inclined, and the Latin-derived word for flat, which is plane, to come up with this phrase. So if you're allergic to elevators, why don't you take the inclined plane?
Eureka!
The story so far. A machine is something that helps you use your energy more effectively. One of the simplest machines is the inclined plane, which allows you to trade increased distance for decreased effort or force. By doubling the distance you move a thing, you can half the force you need to exert. And now, the lever. If you're sitting on a teeter-totter, looking for someone to teeter-totter with, and then a big fat guy comes along, what do? Do you want to risk it? Now, there's an easy way you could have avoided that. Two easy ways, in fact. You could have either have asked the fat guy to move nearer and nearer to the middle of the teeter-totter until you balanced. Or else, you could have made a little adjustment to the teeter-totter before he sat down on it. And then, you would also have balanced. Both methods really boil down to the same thing. You see that support the teeter-totter is resting on? Well, scientists have a fancy word for that. They call it a fulcrum, which is simply Latin for a support or pivot. Anyway, whether the fat guy moves himself closer to the fulcrum, or whether you move him closer to the fulcrum by moving the teeter-totter, the result is the same. The distance between him and the fulcrum becomes less than the distance between you and the fulcrum. And that's the secret of successful teeter-tottering with people heavier than yourself. Or for that matter, the secret of the successful balancing of any object with any other heavier object. If you want to balance a 100 Newton weight with another 100 Newton weight, you place them both at an equal distance from the fulcrum, let's say 2 meters. But if you want to balance a 100 Newton weight with one that's twice as heavy, you move the 200 Newton weight nearer and nearer the fulcrum until it's in just the right place for the two weights to balance. Now you know how to lift a 200 Newton weight with a force of only 100 Newtons. It looks as if you're getting something for nothing, doesn't it? But you're not. Don't forget that the 200 Newton weight is nearer to the fulcrum than you are. How much nearer is it, in fact? 1 meter? So the distance between you and the fulcrum is exactly double the distance between the 200 Newton weight and the fulcrum. That means that you have to move your end of the teeter-totter exactly twice as far as the weight moves. You exert a force of 100 newtons through 1 meter in order to lift a weight of 200 newtons through half a meter. What you win on the force, you lose on the distance. Sound familiar? Of course. It's precisely the same principle as that of the inclined plane. When you double the distance, you can half the force. This is true whether you're using an inclined plane or a teeter-totter. Only we should stop calling it that, because when we use it to make work easier, it's really another sort of simple machine. It's really a lever. Yes, a lever. You use levers all the time, things that give you leverage. After the inclined plane, it's the commonest simple machine in the world. Even cavemen knew about levers. Not to mention old Archimedes in ancient Greece, who was actually the first person to state the principle of the lever. The longer the arm of the lever to which force is applied, the less that force need be. In fact, he got so excited about this one day that he said, "Give me a fulcrum on which to rest, and I will move the earth." That may have been taking things a bit too far, but at least you now know enough to go down and apply Archimedes' principle of the lever to your teeter-tottering.